Welcome to the Explainer. Get your red pens ready because today we are doing a full exam autopsy. It's time to stop guessing and start mastering. If you're tackling Cambridge O-Level Physics 5054, you need way more than just a list of formulas to memorize. You need the actual marking scheme secrets, the little details that separate an average grade from an A star. So, let's step right into the grading room together. We're going to see exactly where students drop marks and, more importantly, how you can avoid falling into those exact same traps.
Here's our test paper syllabus for today. We'll be tackling the big four equations, the golden rule of units, and grading a classic lift problem. After that, we'll expose the kinetic energy trap, weigh ideal physics against reality, and wrap the whole thing up with a final exam challenge. Let's dive in.
Section 1. The Big Four Equations.
All right, consider this the absolute foundation for grading any physics exam paper in this unit. Welcome to the Chalkboard Masterclass. Imagine we're sitting in this high-stakes grading session, staring down a massive stack of submitted exam papers. Basically, everything in the work, energy, and power unit boils down to a few core concepts. If you don't know your basic tools, well, you can't build the house, and you definitely can't pass the exam.
These big four equations literally dictate the structure of every single correct answer. We've got gravitational potential energy, which is mass times gravitational field strength times height. Then kinetic energy. That's 1/2 times mass times velocity squared. Work done, which is force multiplied by distance, and power, which is just energy divided by time. Oh, and definitely don't forget efficiency down there at the bottom. That's useful output divided by total input multiplied by 100. Honestly, you should write these on the inside of your eyelids.
Section 2. The golden rule of units.
Okay, let's talk about the single most critical pre-calculation rule. All that beautiful math we just reviewed? Yeah, it is completely useless without the right foundation. I really cannot stress this enough. Imagine my red grading pen hovering right over your paper right now. Your final answer is dead on arrival if you don't check your units. These equations, they only work with standard SI base units. You absolutely must convert mass to kilograms, distance to meters, and time to seconds before you calculate anything. Failing to do this, it fundamentally breaks the formula and costs you vital marks right out of the gate.
Section 3. Grading the lift problem.
Let's open up our first submitted exam answer and see how these theoretical equations are actually applied under pressure. Here's question 1. We have an 800-kilogram lift raising passengers vertically. It travels a height of 15 meters in a time of 25 seconds, and the power input from the motor is 6,000 watts. The exam is asking you to calculate three things: the useful output energy, the useful output power, and the lift efficiency. Now, the crucial question for us as graders is, where do students usually drop marks here? Look closely at those numbers. Are the units correct? Well, yes, we have kilograms, meters, seconds, and watts, so the trap isn't in the units this time. Challenge yourself for just a second. How would you calculate the useful output energy and power from these exact figures?
If you did it perfectly, your final efficiency answer should be exactly 78.4%. Did you get it right? Let's break down the actual marking scheme step by step and see exactly where those points are won and lost. What's really fascinating here is seeing how the examiner actually awards the marks. First, you calculate the useful energy gain using gravitational potential energy. So 800 times 9.8 times 15 gives you 117,600 joules. Boom, that secures 2 marks. Then for useful power, you just divide that energy by the 25 seconds it took, which gives you 4,704 watts. Finally, efficiency. 4704 divided by the 6,000 watt input times 100 gives us that 78.4%. And let me just add a mild note of exasperation here as a grader. Efficiency can be a decimal or a percentage, sure, but an answer over 100% literally breaks the laws of physics. Please never write an efficiency greater than 100.
Section 4. The kinetic energy trap. All right, we're opening the next exam paper now, and I can tell you right off the bat, this one features a very common, incredibly frustrating calculation error. Here's the scenario. A 1,200-kilogram car is traveling at a speed of 25 meters per second. The brakes are applied and it comes to rest. You need to calculate the kinetic energy, state what happens to it, and name 2 energy stores that actually receive it.
I want to slow down dramatically right here because this is a massive trap. A typical student answer will look like this: 0.5 times 1,200 times 25. This is the mistake I see over and over with my red pen. Do you see it? Students constantly forget to square the velocity. An error here immediately triggers a mark deduction. A true A-star answer correctly squares the velocity, 0.5 times 1,200 times 25 squared. It is absolutely crucial.
When you calculate it correctly with the squared velocity, it yields 375,000 joules of kinetic energy. Beautiful. Now for the explanation parts. When that speeding car finally stops, that massive amount of energy doesn't just vanish into thin air, right? It's transferred or dissipated. But where does it actually go? Well, the receiver stores our thermal energy in the brakes and tires and sound energy from that loud screeching halt. Securing these explanation marks is all about tracking the fate of the energy. Section 5. Ideal physics versus reality.
Let's shift our grading focus from perfect, ideal math to the messy real world, using friction as the ultimate mark stealer. Let's analyze this newly submitted answer. We have a student pulling a heavy box over a distance of 12 meters. They apply a pulling force of 80 newtons, while friction aggressively pushes back in the opposite direction with 30 newtons. The task is to calculate the work done by the student, the work done against friction, and then mathematically explain why the student's work is greater than the useful energy gained.
Let's see how this builds out. The student's total work is 80 newtons times 12 meters, which equals 960 joules. The friction work is 30 newtons times 12 meters, equating to 360 joules. That 360 joules is effectively wasted as heat and sound. Now here is the insider cheat code. To get that final exclamation mark, you must explicitly state that extra work is required, specifically to overcome friction. Just saying energy is lost isn't enough. You must name the exact culprit.
Understanding this ultimate secret to scoring high really comes down to a simple blueprint. You see, in ideal physics, 100% of energy converts perfectly. Total work done exactly equals useful energy gained. It's neat and tidy. But we live in the real world, where work done is always greater than useful energy because of friction. Power in is always greater than power out. To score maximum marks on your exam, always identify exactly where that lost energy went.
And you know, we can connect this reality check to massive real-world systems too, like hydroelectric power stations. Let's cleanly trace the physical energy chain step by step. Step 1. Gravitational potential energy from the stored water. Step 2. That transforms into kinetic energy as the water physically falls and spins those massive turbines. Step 3. That kinetic energy finally becomes an electrical transfer sent to our homes. By linking the energy type directly to the physical object, you nail the sequence. Oh, and bonus points, it's renewable and produces no greenhouse gases, which examiners absolutely love to see you state as an advantage.
Section 6. The Final Exam Challenge. We are concluding our rigorous grading session today with a final multi-step problem to test if you can actively avoid all the traps we've just talked about. Let's walk through this final 3-star challenge together. A machine receives 12,000 joules of energy every single second. Its efficiency is exactly 65%. Calculate the useful power output and the wasted power. Okay, here's the trick. 12,000 joules per second is exactly 12,000 watts. Energy per second is the literal definition of power. There's no extra math needed for time. So 12,000 multiplied by 0.65 gives us 7,800 watts of useful power. Subtract that from the total input and we easily get 4,200 watts of wasted power. Smooth, simple, and full marks awarded.
So, having mastered the marking scheme today, my final provocative thought for you is this. When you look around the real world, can you spot where the invisible energy is being lost? Next time you accidentally drop a heavy textbook or see a car screeching to a halt at a stoplight, try to actively visualize those invisible energy transfers we just graded. Master these transfers, respect the golden rule of units, always watch out for that kinetic energy trap, and you will absolutely crush your physics exams. Keep observing the real world, and I'll see you in the next explainer.